Okay, this slideshow is on mutually exclusive and independent events. There's nothing that new for AP Maths here. Obviously, mutually exclusive means that it can't be in the same set, and so your intersection is equal to 0. And independent events through school in normal maths would be the probability of A intersection B is equal to the probability of A times by the probability of B. There is one other option for something to be independent, and that is if the probability of A given B is equal to the probability of A. Then the two events are independent, which is quite obvious because it means that B didn't actually have an effect on A. So therefore, the probability of A given B should still be the probability of A. So this little formula can come in handy if they're asking you whether the events are independent or not. All right, so this question was asked 2 years ago. Two events, A and B, are such that A and B are independent, okay? So there's the probability of A, the probability of B. With the aid of a Venn diagram, prove that A and not B are also independent, okay? With Venn diagrams, we obviously want to put in our intersection first. So our intersection, because they are independent, is X times by Y. Right, which means I can fill in everything else. So the probability of A is clearly X minus the intersection. The probability of B is Y minus the intersection. Okay, now a lot of people spend some time trying to find what was missing over here. Right, the question is prove that A and not B are also independent. Right, so we want to work out what is the probability of A times by the probability of not B. So the probability of A is clearly X, and the probability of not B, right? Not B, we don't have to go through all of this adds up to 1 or anything like that. The probability of not B is clearly 1 minus Y. It's not B. So therefore, the probability of A times by not B would be X times by 1 minus Y, which is X minus XY. Right? Now we want to check and see if the probability of A and not B, so the probability of A and not B, on our Venn diagram, if we look at it, the probability of A and not B, it's got to be in both A and not in B, would be X minus XY, and therefore they are independent. Okay, then another sort of past exam question. Given that the probability of A given X is 0.5 and the probability of X is 0.6, calculate the value of the probability of A intersection X. So this, whenever you get given something like this, you want to go to your formula, and the formula is the probability of A intersection X over the probability of X is the probability of A given X. So, and now you want to fill in your values. You want to put 0.5 in, 0.6 in, and you can find out the probability of A intersection X, which is your intersection, if you wanted to put it as a Venn diagram. Then they say if the probability of A is 0.5, what can be said about A and X? All right, so what can be said about A and X? If the probability of A is 0.5, so the probability of A is 0.5. If you have a look at it, the probability of A given X is 0.5. They clearly are independent because X didn't have any say in it. Okay. This question is quite a nice question, and I thought I'd give it to you. It's a tree diagram. It could easily be asked in your paper 1 exam as well. All right, but it was a nice sort of AP question. So Joe and Chris play a game in which they each throw a dice in turn until someone throws a 6. The person who throws the 6 wins the game. Joe starts the game. Find the probability that she wins. Okay, so a question like this, you kind of want to get started. So the probability that Joe wins on the first go is 1 over 6. All right. So the probability that she throws a 6 is 1 over 6. The probability that she, so I would definitely put this as a tree diagram. Probability of Joe winning is 1 over 6. But if she loses, the probability of her losing is 5 over 6. If she loses, it's Chris's go. Chris goes, the probability that Chris wins is 1 over 6, and the probability that Chris doesn't is 5 over 6. But then if Chris doesn't, Joe goes again. All right. So if we want to map this out as a tree diagram, the probability that Joe wins on the second go means that she has to lose, Chris loses, and then Joe wins. So that's 5 over 6 all squared times 1 over 6. So the probability that she wins on her third go would be lose, 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 Chris loses, and she wins. So we're looking at sort of a pattern here, right? So when does this finish? And you think to yourself, okay, well, the probability that that Joe wins is clearly either on the first go or on the second go or on the third go or on the fourth go. And you're looking and you're thinking, okay, well, when did she win? And if you look at this, you can see that this is a nice little geometric sequence. So in a way, we know that the A value is 1 over 6. R is actually 5 over 6. And we could look at the sum to infinity. And sum to infinity here would be 6 over 11. Okay, again, get practice in this, the tree diagrams using conditional, or your Venn diagrams using conditional, and generally they're quite quick and you can answer these questions quite quickly.